We are live here yet again. Another week, another time. Let's see. 4th of July. 4th of July was a ton of fun. This was the first year where I really got to get out and do a bunch of fireworks stuff with the kids and just had an absolute great time. Where we're at, we're surrounded by a bunch of fields, and while we're not in a drought this year, like we have been in years past. So we weren't in a burn ban, so we could actually do legally some fireworks. First time in several years. We still keep everything kind of small, right? Because they're just the chances of having one of our fields take off is just not been there, done that. Not interested. Anyway, it leaves room for some really fun fountains and stuff because we've got a good driveway that we could put stuff in. Kind of keeps everything away from the grass. Uh, it worked out really well, right? Ton of fun. The kids just had an absolute blast, which we did the show in Fredericksburg as well. So they do a big show out at the county airport. That basically the whole town, half the county comes to, and it was a good time. Like it's always fun just to kind of sit around and see everybody playing and do their thing, and then go home and do a few of our own. Kind of have some fun with it. Make a late night. Yeah, it was fun. It was a nice time. Kind of just very chill. Something we need a lot more of. Need a lot more just kind of chill. Um, Either way, had a great weekend. Got a lot to do. There's a lot stacking up on the docket. We've got several major projects going here for the training center, trying to get ready for August. There's a lot of there's just a lot happening, and it's okay. Like I'm not complaining. These are great problems to have. I'm very thankful, very blessed to be in this position. Just kind of talking openly and just you know, it's it's a lot to keep up with. But we're doing it. We're here, we're punching through every day, um, just day by day. We're just gonna keep going day by day. I do have some really fun. So I've got several videos actually already filmed, just due to schedule. Getting to them has kind of been slower than I wished. I do have a couple of fun videos I want to do. Um, not I keep saying fun as if I didn't enjoy the others. One of them I have on my plan is I want to get all my pumps set up. So I've got an open end or end suction pump, a vertical, and now I've got a double suction split case. And I'm going to do a whole video just kind of opening them up, getting them cleaned up a little bit and prepped for showing so that as you come in, that gives you something more to look at. You can see what the actual internals of these things look like. At the same time, I'm hoping they get to start this week. I'm having a set of fabricators build some stands for the YT compressor I have. And so if everything works out in the next couple of weeks, that will be ready. And we can get our YT in here, and that'll be another display piece that again we just look at, we can play with. You want to tear apart the rotor housing and just see what it looks like inside, by all means tear it apart. So anyway, today we're repping the ICE group. Really incredible group of folks. For everybody that is an ICE member out there, thank you for joining. Good to see you. So I've already got some stuff scheduled technically for this year's conference, so I'm not going to get to make it to the ICE meeting, unfortunately, at least as it stands right now, unless something changes between now and September. It doesn't look like it's going to happen this year. I did get to go last year. I'm hoping to get to go maybe next year. Anyway, and then we got Southwest Mechanical. So these guys are based out of Vegas, and so really had a fun time out there with them, working with them. Spent an entire week, I think, or just shy of a week, right at a week, something like that. It was a good time. Is a fun place to be, and I don't mean fun as in like the Vegas party scene. Of just kind of getting to work with actual locals when I'm there, not being in the tourist side of things, but actually get to see the local side of it and get to meet just proper local folks out there. really enjoyed that time. Anyway, if you want to get your company represented, just something I'm just having some fun with right now. I am requesting T-shirts and even hats. So if you want to get your company to where this is going to be my thing going forward, where I'm collecting basically merch or company apparel, and this is just going to be my attire. And my goal of what I want to do with this is, like, we are a community. I am here doing my best to just represent us as a community and as a body to move forward. With that being said, part of that representation is like actually wearing y'all stuff and representing the teams that you work within. And so, yeah, that's what I want to do here. Anyway, I'm rambling on. Let's get into some questions. And I do see we have there's one question about cooling tower and humidity, and that actually aligns perfectly with the first question I plan to dive into. It's good to see everybody. Thank you for joining. My friend, can I ask why from 95% to 50 to the oil level going down during all? Oh, yeah. Okay. Yeah, we'll dive into that. So you're seeing a migration issue on your oil, 100%. Let's start off with this. This goes right into the very first question in the chat here. And then, let me change one setting. Make sure we see everything. There we go. All right. 60-degree tower water in the summertime. Bunch of question marks. And basically, so something that we have to understand with cooling towers is how we're able to achieve the water temperatures we have. So using this tower as our example, all right, this would be a very common style that we would see from in a lot of applications. So this would be a counter flow. So airflow is coming out the top and the water is draining down. And because of that, the actual water and air counter to each other instead of a cross flow. It doesn't really matter which style of tower you have. You're limited by the wet bulb of your space. And so wet bulb is our most critical factor when it comes to our cooling tower. In addition to, like, yes, cleanliness, things like that also play a factor. But wet bulb is what we have to pay attention to, which gets back into psychrometrics. And when I talk about, like, I'm not worried about what our dry bulb is, which is our sensible temperature. That's what you're going to measure with a regular thermometer. And so this is what makes it possible to where if we have the right conditions, there are plenty of places that are basically just dry, right? So they don't have a ton of humidity in the air. They may have really high dry bulb temperatures. Your sensible just outside air temperature could be really high, but because you're so dry, the humidity is really low. And because of that low humidity means low wet bulb. Low wet bulb means that we are able to create evaporation at a lower temperature. So the temperature at which we can evaporate down to. I don't know if that makes any sense or not. Ultimately, so if you don't know, this gets into what we would study with psychrometrics. Psychrometrics is just the properties of the air and how they interact, right? So that's where we get sensible and relative humidity, so your RH, wet bulb, dew point, pounds of moisture per cubic foot, yada, yada, yada. Like, all that's built into a psychrometric chart. If you're in a situation, and getting back to the core question here, and this gets into the question in the comments here, if we're in a situation where we have a 60-degree, or if we are in summertime and we have a humid environment, the likelihood we're going to achieve 60 degrees of tower water, because, like with our wet bulb, is unlikely because of the higher humidity. Period. So no, there's no way that in the summertime, in those circumstances, you're not going to just magically be able to achieve that kind of tower water temperature due to higher wet bulbs, unless you live in a more dry and arid environment where there's less moisture in the air. Some examples I could give with this would be like in the United States, in the Arizona type regions. So I know that out there specifically in the summertime, as hot as they get, they have periods where they dip in humidity significantly. And especially, I think, in the evening time or somewhere in that ballpark in terms of like time of day. So their wet bulbs, from my understanding, will spike like during the day because of the heat. But as the evening cools back down, everything cools back down, the wet bulb temperatures drop significantly. And they are able to produce those lower tower waters and get that better efficiency in those evening periods. Somewhere in like my area where I'm at in Central Texas, we have so much humidity here that during the summertime we're just not going to achieve these numbers. Now, we can do it in some parts of the fall, we can do it in some parts of the spring, and sure, we can do it in the wintertime just because it's just in general cooler and typically drier. But we're not going to achieve that in my region on a even overnight. Most of the time we just don't have our wet bulb temperatures drop that low during this time of the year. So it really becomes seasonal dependent. What's important here is just not to write off, oh, just because we're in summertime that's not going to happen. That really does become regional specific. But beyond just being regional specific, there will be times where it could be possible for your region if you're in the middle of a dry spell. Like that's the whole thing we have to keep in mind with this. It is fully dependent on where our wet bulb temperature is. Now, if we get into just how to like calculate this real quick, it comes back to tower approach. Okay, I'm going to summarize all this really quickly, and then we're going to dive a little bit deeper into the comments there. So our tower approach, this is the difference between our wet bulb minus the tower leaving water temperature we can achieve is wet bulb minus the tower approach that we're designed for, gives us our leaving water temp out of our tower, right? This is what we can expect. Or I shouldn't say minus, I should say plus. Wet bulb plus tower approach gives us our, and so you would reverse this around. You could say, okay, what is my wet bulb? And then subtract that out of, I guess the better way to do this, you take our tower leaving water temp, LWT, subtract your wet bulb from that, and that gives us our tower approach. I said a P there a second ago. All right, TA, tower approach. So this would be just two different ways of working that forwards and backwards. Every tower has a design approach value. It's typically somewhere between 5 to 10 degrees Fahrenheit, most towers. And that's going to be when they're clean, so keep that in mind. The dirtier the tower gets, if the fan is having issues, if we're having water treatment issues, if our louvers or our deck is not able to flow, or if our nozzles aren't properly spraying appropriately, we have broken nozzles, clogged nozzles, like all those little things, whether it be an open loop, closed loop. Typically, we're going to be dealing with open loops in our environment. But you will come across closed loops eventually, on occasion, if you get far enough into this journey. In a chiller application, you'll run into closed loops more often in like self-contains and other applications. But for chillers, we're usually dealing with an open loop. So all of those little things, like I've had it before to where I walked up on a service call and it was a open loop counterflow, but the nozzles, like several of the nozzles on the spray rails were completely broken off and they weren't like fanning out properly. So they were just a straight jet stream of water, and that was causing tower water control issues because we weren't properly spreading that water out. It was just a jet stream basically shooting straight down into the basin through the fill. went in, replaced those nozzles, got everything fanning out better. Then all of a sudden we were able to start maintaining temperature properly. Okay, so all those little things play into this approach value getting worse and worse and worse. Most towers, in my experience today, that we will deal with are usually going to be closer to that 5 to 7 degrees when they're functioning well. But there are some that are genuinely designed for more of a 10-degree approach. So you just have to build that into what you expect this tower to be able to do. Okay. My goal here is just to kind of push back on this mentality that just because it is summertime doesn't mean you can't achieve these values and these numbers. That is not the time. The being summer is not the core problem. Now, having high humidity, which gets right into our next conversation here, is the real issue. We have a high humidity state. So let's address that. Okay. Yeah, I'm just going to read this off and then let's just discuss it. So Middle East summertime, too much humidity, that way cooling tower water temperature in condenser inlet, too much high temperature of water. Okay, so our condenser water temp entering the machine, entering our chiller is high. That chiller how to control for high discharge pressure. And chiller is going into a surge condition. Okay, so you're dealing with surge conditions, but you can't get your tower water down. First, understand that this is a scenario that we constantly face across the industry, right? So you're dealing with a very routine problem. We cannot physically control our tower water to the degree that we need to for whatever reason, and we're dealing with surging. Now, keep in mind, the less load a machine has on it, the easier it is to surge. And there's going to be times where I would recommend, from a controls perspective, if you've got multiple machines online but they're running at part load, shut at least one of them down and put more load on the others. Now we're talking about centrifugals here. So just based on the fact that we're discussing surge, let's keep that in mind. We're discussing a centrifugal, period. And for a centrifugal, you will benefit by having a higher load on that machine that is surging, as long as you can maintain your tower water. The best thing you can do in this case is to give that machine, that compressor, more load, more flow, and that's going to push you off of that surge line. And this is assuming you've got multiple machines on and you're running in a part load condition. Now, there could be other cases where there may be more going on than just a load issue. But one of the most common ways we deal with a surge problem comes back to lift with part load. We're not allowing that machine to fully load up. So that would be my step one. Do we have multiple machines on at part load? Now let's simplify this, and let's say we have just one machine running at a decent load. And when I say part load, I mean anything less than design load, right? So if your design evaporator TD at your GPM was supposed to be 10 degrees TD, but you're only running 7 or 8, well, you have a little more room. Now, technically, that's still a really good load for that machine, but you have a little more room. And so if you could get closer to that 10 degrees across the evaporator with high condenser water, so we're just assuming that there's not a way to get that condenser water down. Let's just say you're running 95 degrees entering water, which is going to be high for a lot of machines. But if you can get that evaporator load up properly, you can find a sweet spot. And I guess let me just draw this out. We're just going to bring this as example just in case I use it. So it comes back to just managing our lift and our surge, our lift to flow graph, our surge map, surge graph, however you want to say it. So we have lift. Lift is the difference in pressure across the compressor. Okay, so suction pressure minus discharge pressure, the difference there gives us lift. Okay. We could also look at this as saturated lift. So evaporator saturation minus condenser saturation gives us our saturated lift. I personally prefer to operate on this saturated lift front. Either way, lift is just, that's what it is. It's lift. Another way to think of it is just your differential pressure. So then over here we have flow. Okay, this is the physical flow through the impeller. So as we open guide vanes and we get more refrigerant flowing into the eye of the impeller, so the total, as CFM through the impeller of refrigerant increases, we are increasing flow. It's as simple as that. So more load, moving more BTUs through that particular machine increases our ability to, or increases our total flow that we're going to need through the machine. So let's say our surge line is doing something like this. Okay, that's our surge boundary. And right now, let's say you're operating at a part load condition. So say you've got 7 degrees across your evaporator, and you've got a high lift. Okay, so we're going to assume a high lift, and you're running right here at 7 degrees across the evap. Now, full load could technically take us over here. All right, so this would be like our maximum flow rate that this machine could be designed for. Okay. Well, if we're able to increase that load on the evaporator, so we've confirmed we have proper GPM all the way around, right? So from a GPM perspective, we are running at design GPM. That's not changing. But by increasing from that 7 degrees across the evap to 10 degrees across the evaporator water temperatures, now we've had to increase flow to over here. Now by increasing this, we have very likely increased lift just a little bit because we are putting more, we're doing more work in both heat exchangers, the condenser and the evaporator. So we're going to increase lift ever so slightly. Okay, so now lift has increased to up here, but because we increased flow, now we're back off of that surge line, and this machine can cruise there all day long. This is assuming, right, in a scenario where we have really high condenser water temperature and we cannot get it down. One of the best methods is, okay, well then we have to have more load on this machine if we expect it to be able to run without surging. Okay, if you want it to run without surging, which is our goal, yeah, it's got to have enough load on the evaporator. Now from here, if it's not something like this where we're balancing the surge map or surge graph, then we get into, okay, do we have a refrigerant charge issue? Do we have we verified flow? Like we start getting into a lot of the other basics that exist. What do our approaches look like? Do we have clean tubes on both evap and condenser? Are we dealing with an oil migration issue? Is our eductor set correctly? Is our eductor filters flowing correctly, or are they getting plugged up? Have they not been changed in a while? If we're dealing with a low pressure machine, do we have non-condensable stacking? So in terms of we're surging, but we have high condenser water temperature, it's possible that that surge could just be the result of other things. You can't get the tower temperature down, fair enough. Is everything else in order? So this is where we would need a little more information as to what is causing, or what does our data log look like and what machine are we dealing with. Are we talking a CTV or a YK? Now, you've been a part of the channel here for a while, so I know you've got some YKs. So I am leaning in a lot of my description into the YK side of this, because I know that's when we've talked in the past, that's been the machines that you've typically referenced is a YK within your plant. So then I would have to see what the data log look like, and does that data log indicate an issue somewhere else? So getting specific to the YK in this scenario, like on my evaporator and condenser, like I don't really want to see more than 4 degrees. So less than 4 degrees Fahrenheit of approach on evap and condenser. Okay, so when I say that 4 degrees is being really generous, I really don't like to see above 3, but I have had it plenty of times where the machine is under perfect circumstances and it's running about a 3.5 degree approach. Now keep in mind that half a degree could just be the difference in a sensor's calibration. So being generous, we can say as long as your heat exchangers, your condenser and evaporator, are running a less than 4 degree approach, which a YK would call a small temp difference. So the small temp difference on your YK is less than this, then I would say you're exchanging heat well enough. This would be probably the number one thing I'd want to verify next in my process. Where is my approach values? And this is assuming I've already verified GPM. If we haven't verified our GPM or the DP, or differential pressure across the inlet to outlet of both our condenser and evaporator, right? That has to be done. We have to verify DP. Then we can verify the approach once we know our flow is correct. And if approach is not good, then why is it not good? That gives us a thread to pull on, right? So it's just start with very simple steps and dig deeper with each one. So do we have, so like so with a YK, running a high liquid level is going to increase a condenser head and it's going to increase approach, right? So that just gets back to, are you running too much liquid level? The solution is not to just drop the liquid level, by the way. Okay, so you drop that liquid level too low in a YK's condenser, you're going to cause issues with the subcooler. You're going to get subcooler seal loss alarms. That's not good either, and you will eventually rub a hole in its rack, a subcooler rack. But don't want to do that. Yeah, so I guess I could sit here for a while and run down a whole list of things. I'd really just have to know, what is this approach doing on both sides of the system while we're having an issue? What is our evaporator load? What actual condenser water are you running? At some point, there is a ceiling. Like if you're having to run 100 something degrees condenser water, I don't know that you have, like, just at that point you don't have, you need to fix your tower. Like if that's the case, like if your tower water is truly that high, I would assume that your tower approach value is that high. So that would be okay. That's a good point. We also, in addition to our heat exchangers on the chiller, we need to know what our actual tower approach is. So if our tower approach is getting too high, like we can chase problems all we want at the machine, at the chiller, but we gonna have to figure out how to fix the problem at the tower. So I would ask just a lot more actual like operating data on what we're dealing with. What are your approaches? Have we verified GPM? What does your tower approach look like? That would help us get a lot more information to give you a better response. Right now, I'm very limited in just how far I can go, but just these are things to keep in mind. Our surge graph is the case if everything else is perfect. Tower's perfect, the chiller charge flow, all that's perfect. Then we still have the limitations of this surge graph. and we have to work within its boundaries. If things aren't perfect, because the less perfect things are, the more the charge is having an issue, the more heat exchange is having an issue, yada, yada, yada. The more of those problems there are, the more difficult we're going to have working within the boundaries of this surge graph. So we have to fix those things if we want a path forward. Good to see everybody. Good to see you, Sterling. It's been, it was good. We had a good time. Yeah, how has that heat wave been going for y'all? I heard about y'all getting hit by it, but I haven't looked into it too deeply. Working with a YK 5,000 ton. Cool. All right, let's see. We got some good questions coming in. Let me dive into our next one here. Let me just keep this train rolling. Give me 1 second. Okay. Asking why from 95% to 50 or 40%, the oil level going down during operation. Now we don't know like a model of the machine or anything like that, so we're gonna approach this from a principles perspective, which is the most we can do. Using our machine here. All right, so at 95% load, okay, so we're saying that the chiller's motor at 95% is maintaining oil levels. This will be our oil pot in this particular machine. All that's running perfectly fine. At the moment, our machine unloads down to 40 to 50% of motor current, which is just reflective of reducing total load on the machine. We begin to lose oil level in our reservoir. That is a classic case of just having a migration issue at lower loads. So then the main focus becomes our eductor system. So it is very possible that we are how do I want to say that? We don't have enough velocity going through the system in order to get the oil level back. Okay? So keep in mind, when we have an eductor, all these machines are using some kind of eductor. The only ones that don't is like the RTHD and WD series and RTUD by Train. So those are some water-cooled screws. They use a thing called a gas pump. It's a bit different. But outside of those, we're using some kind of eductor assembly. So with an eductor, what we have is a discharge gas inlet coming into a nozzled chamber. Okay, so it's flowing in and it hits this nozzle. Now this nozzle is causing a pressure reduction on the other side. So we've got this pressure drop as we come into this next chamber. Okay. We are then taking a little, we're coming off of the liquid level on the upper parts of our liquid level on our evaporator, because in these particular machines, so I'm assuming we're dealing with a machine that has a flooded or falling film evaporator. Okay, if you're dealing with a DX or a brace plate evaporator, it's a slightly different conversation. If you do have some more details on your particular machine, that will help me better focus here. but I'm going to approach this from you've got a flooded or falling film style evaporator with this, okay? So that means that we have a line coming off of the top level of our liquid refrigerant in the evaporator specifically. Now keep this in mind. Some evaporators run really low liquid levels. So if you see this oil return line for the adductor coming off the bottom of the heat exchanger, that's because you've got a really low liquid level. But in other versions, you're going to see it coming higher up off of a midpoint off the evaporator. So instead of pulling off down here at the bottom, it's going to pull off further up here towards the middle. That just means that it's because we're running a higher liquid level in that heat exchanger. Okay, so this is coming in, and because of this nozzle creating this low pressure zone, we're utilizing the Venturi effect, which is allowing us to siphon that low pressure liquid oil mixture, because your oil is going to collect at the top of your evaporator, just period. So because that's where our oil is collecting, we are going to we need to draw that liquid oil mixture off the top of the evaporator liquid level, top of the evaporator liquid level, and allow that to be re-siphoned back into the oil system. Okay, that is our ultimate goal. So as these two pull in, what we get is a high pressure vapor on this side, a low pressure liquid oil mixture on this side, which then creates a medium pressure oil latent mixture here. Okay. This could feed to wherever it goes in the system. So in many cases, this is going to the reservoir. This could go back into the suction line. And like on some of the air-cooled screws that we have, this just feeds back into the suction line of the compressor. It could feed just back to the compressor shell. So we've got many compressors that this just feeds into a oil return port on the shell of the compressor, which is technically on the suction side, or it's on the suction side of the compressor, but it bypasses the motor. Most of the time when it ties directly into the compressor housing, it's not actually going back through the stator. It's just coming into the compressor suction, the true suction. Or in in our centrifugals, usually our oil sump is on the low pressure side, right? So with a screw, we usually have the oil system on the high pressure side. With a centrifugal, our oil system is on the low pressure side of the system. So that being said, we may have this return back to that reservoir. Okay, so in this particular case, it just come back into here, getting pumped through the adductor assembly. Another way to say adductor is a jet pump. So if you're familiar with the term jet pump, that is what this is. Now, what is important, why I go through all this, what is important when we to make this system function is we have to have enough velocity on our high pressure side. We also have to be set correctly at our liquid level here. And something to keep in mind is as we have our machine load and unload, the refrigerant levels and volumes can shift and fluctuate a bit. And so whether it be the actual refrigerant level, again, not knowing what machine you're physically working with, whether it be the refrigerant level itself has adjusted and now maybe we're not picking it up correctly because maybe we've dropped down below the pickup tube, or we've reduced too much velocity. And it could be to where, and I have seen this, where the adductor filter, when it begins to get clogged up at high loads, there's enough velocity and force going through the filter that it will still kind of do its job and return oil. And as the machine unloads, because the filter is getting clogged up, it can't move through the filter correctly. And so that starts causing an issue, and you just need to service your eductor filter at that point. So I have seen, like, it's just one of the possibilities. But one, we have to make sure that we're maintaining enough head pressure to have high enough velocity. We have to make sure that our pickup tube is still set correctly. And some of these are field calibrated. So this is another thing to keep in mind. You on several machines, you have to adjust that eductor line manually as part of the startup process. These are things that we should be checking. And so if it's not calibrated correctly or set just right, it may work great when at load, at higher loads, but as the machine runs in part load conditions and unloads itself, then it starts having issues because it can't draw enough flow to keep that oil recovered properly. And that's why you're seeing that oil level drop as the machine stays online in a part load condition. So that's the main things I would want to be monitoring for, is the eductor pickup, my velocity, like my actual head pressure difference. Am I maintaining enough head pressure to allow the eductor process to happen in the first place? And is my eductor filter, they almost always have a filter somewhere in this assembly, right? Some of them I've seen it where it's actually filtering, like a YVAA by York is filtering on the input feed side of the eductor. Most of them are usually filtering on the post eductor side. So after it flows through, it processes through the eductor filter there. Either way you slice it, that's going to be my core focus, is these items. And then I'm going to go from there as needed. So yeah, you're seeing a part load migration, which comes back into just general service and calibration of the eductor assembly in the first place. That becomes our main focus. So just kind of wrap up, just why from a 95% load to a 40 to 50%, we see oil levels begin to drop in operation in our reservoir. So we're maintaining them at just fine at 95% motor current. We unload down to 40 to 50%, then we start to see the migration happening. And all of that oil is going to your evaporator. Like, if you don't know, that's where it's stacking. Like, it's going to accumulate there until it is brought back out of the evaporator. Now, just real quickly, if you're dealing with a braze plate or a DX, which means the refrigerant is inside the tubes, the water is on the shell side. So a DX shell and tube. Those are strictly just a velocity thing. You're not maintaining high enough head pressure. Maybe you've got a charge issue. So I've seen that to where you've got head pressure, but you don't actually have enough refrigerant charge. You're going to see higher superheats in that case. So either way, those machines don't have an eductor recovering that oil back off. They don't need one. We just need to have enough velocity and a proper charge going through that evaporator that'll carry that oil back. So either way you slice it, if you're dealing with that other style, just make sure you've got you're maintaining head pressure and you've got a good refrigerant charge, and that oil should be coming back. How you doing, Jason? Good to see everybody in the chats, guys. Hope you're having a great start to your week. We are rocking and rolling here. All right, we got a YK question. Let me read this real quick. 5,000 ton. Offset only 1 degree and condenser and design. Its surge count continuously increasing and sometimes trips on high. Okay. Let's get you spooled up here. Okay. Now, I see we've got some chats going, so I will move to the chat and just kind of catch up with that in just a second. So let me just get started with the question, and then we'll dig through the conversation. I'm working with a YK 5,000 ton chiller, and we are offset only 1 degree in condenser than design, and its surge count is continuously increasing. Sometimes it trips on high condenser pressure solution. All right. Seem like it's a end of design temp is 33 degrees inlet, but the vendor set the fan degree less. Our inlet is 34 degrees Celsius. All right, so I'm assuming your condenser design was designed at 33 degrees. Well, also keep in mind those design temps are like at max load. And so, which 33, here, I can do some math here. 33 Celsius to Fahrenheit. Yeah, that's what I was thinking. It's about 90 something. Okay, so that's basically 91. So you're running, what, 92, 94? See, it's 34. You're actually running 93. Yeah. So, yeah, those design temps are strictly for like running max load. So this means that you've got maximum evaporator load as well. So if you've got a 10-degree TD design for your evaporator, then you can run up to that 92 degrees condenser water and not have issues. But the problem is as you reduce load on the evaporator, we also need to be able to reduce load on that condenser and bring that tower water down. So while a lot of machines may be designed for 90 something degree, unless you've got a very special application, they may be technically designed for 90 something degrees. Most of the time we're going to run that in a far lower condenser water temperature. We're not going to actually run that condenser water up at that point unless we're running like full load conditions all the time. Let's see, condenser is set for cutoff, but it's tripping around. Yeah, which it's tripping at that lower point. That's, to me, that's just going to be, that could very likely just be uh, a difference in calibration. Or one thing to keep in mind, so this is actually a really important point. The way that YK OptiView panel works, when you see the snapshot that gets taken at that point of alarm, that is taken just moments after the actual event triggers. So it's not a literal at the moment of trigger. There's a slight delay. So it triggers safety, and there's just a slight beat, and then it logs the alarm. So it's what I've seen happen with what you're seeing is you're just seeing the slight time delay of the alarm log being captured to the actual trip point. So it is probably tripping at the set point, and in the process of it tripping and shutting off, you're seeing just that slight just blip of a delay. It's a pain in the butt. Yeah, it's unfortunate that it does it that way. See, we're working with 230 evap flow, condenser flow. Other also trips on chilled water flow switch open. Yeah, so it sounds like this may just be a commissioning thing, to be honest with you. So, all right. Yeah, I would really be interested to know what your, now you said you're actually tripping the high pressure you're tripping high pressure safety, which, let's see, you're dealing with a 134A machine. Yeah, and that 11, let me do another conversion here. 1120 kPa to PSI. Yeah, that's 162 PSI. So what I'm going to do is pull up my ref chart because something sounds off with that. So we've got 134 at 162 PSI. That's 116 degrees. So what that would mean, let me kind of, at the PSIG that you're running, that would mean that our condenser saturation to get to the point of tripping the high pressure is 116 degrees of saturation. Okay. Now, you said you're bringing in tower water of 93 degrees. Now I'm doing this in Fahrenheit and such, so I'm doing the conversions on my end. So this is this is Fahrenheit sat trip. Okay, but we're bringing in 93 temp, 93. So if this machine is truly exchanging heat properly on the condenser side, we should at most be running, which is only 110 psi. We should at most be running let's just give it a 4 degree. So that would be 97 degrees of saturation. So somehow we're getting from 97. This was saying you had full load on that condenser. We're getting from 97 up to that 116 degrees of saturation, which is where we're tripping on the high head. Which, yeah, these machines should not run there. So at what point, like, what is going on? So I guess my current question would be, what is your small temp difference? So that's what the YK is going to be monitoring here. When this machine is running, and ideally before it starts surging, like, what is your small temp difference on your condenser screen? Do you know that number? Other one trips on high. Is there a lead lag type chiller? These are a lead lag. One is 2300, one is 27. Okay, so we got two machines, 5,000 total. One trips at high condenser pressure, the other trips on water flow switch. So yeah, this sounds to me personally as like a commissioning thing. So I really want to know, all right, 1.1 to 1.2. So you're saying your approach on the condenser, your small temperature difference is 1.1 Celsius to 1.2, which Celsius you should be no more than about 2 to 2.5 degrees Celsius of approach. So I just want to confirm, you're saying that is that 1.1 to 1.2 is your condenser small temperature difference on the machine that is tripping high head pressure. Okay, so yeah, so evap is 0.9 to 1. Yeah, so that's part of where something is happening to our flow for that to be possible. So this is where I get to. For us to go from a 97 degrees saturation to 116 like that, if we're actually maintaining 93 degrees which in your case, if you're actually maintaining 34 degrees Celsius of entering condenser water and you're not seeing that condenser water rise, like it's actually stabilized right there at that, then but your approach is also stable, right? So your tower water inlet is stable and your approach is stable, but somehow we still end up hitting that trip point. Something is happening to our flow somewhere along the way. So yeah, in terms of my email, yes, I'd love to continue this chat. I will throw it into the chat here. Cool. Um, yeah, send me an email because yeah, this tells me there's has to be a sudden event happening to take us from here to here if these two are stable. Like if being that your approach, your small temp difference is stable, your entering tower water is stable. Like if it were just surging alone, well then we just get into commissioning, right? And that would be the rabbit hole I try to chase. What is going on with our commissioning somewhere in this process? And also, why are we running such high condenser waters in the first place? I'm not saying that you shouldn't be. There are applications where it is necessary, right? Don't get me wrong. But in most applications, we don't actually need to run at those high temps for the condenser side. We want to save energy and we want to be more efficient by giving some condenser relief and lowering those condenser water temperature set points, especially if our wet bulb temperature is low enough and we can get the towers to make colder water. If we can do that, we can save a huge amount of energy, and like this whole surge issue can be significantly reduced. That being said, even running with the numbers you have, it makes no sense to me how you get from this to that. Because you're going from a 97 degree saturation, worst case scenario, right? Which this is overestimating what you're actually doing. So you're actually running at more of like a 95, 96 degree. These type of 9 machines are there. Well, so just here, let me see if the okay. Yeah, I that would be where I go with this because you're even talking about the evaporators triggering on low flow. So being that the on one machine we have low evaporator flow alarms happening, on the other machine we're dealing with high pressure trips, something on the water side commissioning, whether it be how the automation is staging the pumps. So that could be one issue. The pumps aren't staging down. Maybe they're staging off prematurely and there's not a delay. Yeah, the total of 4,500 ton load. This is the full load uh, for 3 plans. So 3 buildings. Either way, it sounds like they're, because I'm assuming this is like you're coming in the mornings and you're finding this, or um, actually this would be a really good indicator. Is this happening where like y'all come in every morning and all the machines are tripped off like this, or is this actually happening during the day, mid operations, when you would normally have everything fully online? Like, when are you having these alarms? Are they consistently in the morning, or uh, maybe overnight kind of thing? Like, because if that's true, then I really lean into you. The surging is probably a different issue. Okay, that's a different conversation. We can dive into that another time. But in terms of you tripping during the daytime, okay. Yeah. Yeah. Well, just there's getting a full data log. So when you do email me, getting a full data log on both machines. So even if it's just pictures of the OptiView panel, and just give me the high level picture of like where the machine's at. Um, that's going to give us a lot to work with, and then from there we can try to critique it down further. Um, yeah, let's do that. I appreciate you coming though. Like I love everybody loves doing these like in depth kind of back and forth, right? So please don't don't hesitate for that kind of thing. Like that's why we're here today. We're here to have these kind of conversations. Even if we can't come to a solution, the process of trying to get there can be really helpful for everybody. Okay, so we got an RTAF question. Give me 1 second. Let me get this set up here. All right. Has anyone seen a train RTAF with sudden high pressure spike within 7 to 15 seconds, causing a high pressure trip? The issue is sporadic and the refrigerant charge is correct. Any suggestions? All right, I know we've had some chat going on here, so let me catch up on our chat. See, valve fitting, little ring prevents valve from closing on its own due to vibrations. Discharge valve, volume valve is fully open and locking ring is installed. When the condensing pressure starts to rise, the compressor immediately begins to unload. Right, yep. Yeah, because we go into high pressure limiting. Yep, that's right. At the same time, the EXV is commanded to close, but the actual EXV position responds more slowly. Yeah, despite unloading, the condensing pressure continues to rise very rapidly and trips on high pressure. Let's see. Discharge line check valve. I've found recurring overcurrent in compressor current sensing device. Let's see. Could a faulty discharge check valve cause such a sporadic issue? Sometimes the chiller runs perfectly for hours or even days without any problems, and then suddenly condensing pressure. Well, one of the things to keep in mind is you're seeing the let's see, the high pressure switch. I got to remember the high pressure switch on that is that off the compressor housing? Nah, that's a good question. Here, let me look at a schematic real fast. Yeah, let me pull that one up. That's a good point on the high pressure. Let me view the actual schematic because I've got that one saved here. For an RTA. Wait, you said which one are we talking about? RTAF. Let's see. RTAF. That's a carrier. Is it this one? No, that's a 30GX. It's carrier. I'm trying to remember where maybe this one. Yeah, here we go. Well, it's RTHD. Dang it. I gotta label these better. I've got the AF. Saved. That looks like a adductor. Yeah, here we go. Okay, high pressure is pretty sure it indicates it on here. Muffler, valve, discharge. Oil feed. Maybe it doesn't. I thought it indicated on here where that discharge, because I think those have an actual high pressure switch more than just a transducer. Maybe I'm wrong. Maybe I'm misremembering. Okay. Yep. So in terms of could the discharge check valve cause that? Well, that depends on verifying where the sensor is at. I think the sensor on those is on the actual line, which would be post. It's post discharge check valve. So the answer there would be no. You would end up like if that check valve was failing, you would have the motor over current causing the machine to kind of surge, basically, where it's going to spool up and it's going to hammer like hell. So that would be like if we had a discharge check valve issue, I'd expect that constant hammering on the machine on the compressor. Now they can be sporadic because those are mechanical checks, so it can be, but it's usually when they fail, they fail. Let's see. Positive, but you can rule out the possibility of checking if the ball valve holds. Have to recover the charge. It's on the discharge. Yeah, okay. All right. Perfect. Yeah, all right. So I'm caught up on the feed now. So having a sudden spike. Let's see. And those are running. So have you verified that you're not having a condenser fan fail? So those are running. At least all of them I've seen have the newer ECM style modulating condenser fans. And one of the things that's possible with those is while they can fail toward just a direct failure, what they can also have is as they begin to overheat, the module ends up shutting it off before it becomes like an electrical failure. And it's something where they'll randomly shut down and you won't know it. Now, in terms of being able to check that, one of the ways I would probably do it is with a thermal imager. So if I was in that spot, I would get my thermal imager, and with all the fans are probably running at the time, but if we have a fan having a thermal control issue, it's going to just be naturally running hot, period. And we should be able to see that via an imager. So if you walk around, you'll notice that one of the fan bodies is just excessively hotter than the others. And I would use that, or maybe there's a couple of them. So like in my mind, I'm questioning, do we have a couple of condenser fans that are going off on some kind of thermal, and them just suddenly dropping out of the flow is resulting in like a massive, just sudden spike in head pressure. You've already verified the discharge isolation. I don't think it's going to be the check valve because we're sensing that pressure post check valve anyway, and a check valve is going to pose like you're going to have that compressor surge. Like if you've never, I've got videos on it. So let's see. I had a video on a YCAS if you want to go back and look through any of my stuff. If you've not heard a screw with a closed off discharge, because I did it by accident one time, so I actually got it on video. I didn't open the valve correctly, and it was an oops. Point is, like, you can hear what that sounds like. It's not fun. Well, no. So not all the fans have reporting. No. What if, especially those RTAFs, they get fed power and they get fed a reference. So they have power and reference, but they don't have like a feedback or anything to my memory. They're basically being told like we would tell an actuator. Here's a power leg, so they feed them what is it, 120, 240, whatever the motor voltage is. I forget off memory. They're feeding them motor voltage to the fan. So there's two sets of you've got your power in coming to feed the fan, and then you've got your reference coming from the controls, giving the fan its speed signal basically, and then the fans will use that in its internal module to then spin up and run at whatever. Um, so it's not actually monitoring if a fan's functioning or not, like Sterling just said. It doesn't have that kind of feedback. So that's just one. That's just one thing I'd want to verify. Do we have an ECM fan beginning to run hot, causing an issue, and it shuts itself off? Because now, while we have in a normal, just a basic fan, typically we're just going to see. On RTAF, no, there's not a COM bus. So these fans aren't like there's not a COM bus on the fan circuit. Yeah, all condenser fans are running at 100% when the issue occurs. Even if I manually shut the condenser fans off, it still takes more than, yeah, okay, for the high pressure trip to occur. And you're happening within 7 to 15 seconds. So that's an excellent point. Let me think. RTAF with sudden high pressure spike causing a high pressure trip. Let's see, the pressure spike reading, is it red on the display? Or is the cutout just on the pressure switch if mechanical? Something could be out of calibration. That's a fair point. Well, the more I think about it, I don't know that these actually have a mechanical high pressure switch. I think these are relying on the transducer. Y'all can correct me if I'm wrong. But if memory serves, I think these are relying on the transducer pressure specifically. Now, that is a fair point. It could be... it could be a transducer failure potentially, because that is really fast to suddenly spike to the point of tripping. So okay, so they will have a okay. So we're triggering. So yeah, that's a fair point. Like, have we verified that pressure rise is happening via a calibrated gauge? Granted, let's see. Yeah, or just have you had any kind of trending? Well, I mean, keep in mind there's companies that do that. Like they've as just like a lot of machines don't have low pressure switches anymore. There's plenty of them that they no longer have a physical high pressure. They're strictly relying on the transducer to report all of that back. So let's see. Trying to think of a good example to give. Either way, like they exist. Yeah, they have a mechanical switch. So if they have a mechanical switch, have we verified? I mean, it sounds like you've gotten deep enough into this. I would assume you've verified that the switch trip point, we're actually hitting these pressures, and it's not just a false trip. So assuming it's not a false trip, A sudden spike. The machine definitely reads it. It tries to unload. You said that. So it tries to unload the compressor. We have a sudden spike. We're tripping on high head. Let me look at that circuit again. Trying to see what all is involved. Like, where could we have had a failure? We have the adductor. The adductor wouldn't have done it. And these don't have slide valves. These are strictly speed control. So it's not like, so in one, like in an older version, I might think that, okay, well, maybe the slide valve is suddenly moving to a full load position. Even though it shouldn't be, but like these compressors don't have that. These are I'm looking at the wrong schematic, damn it. These are going to be strictly speed. They're speed control only, which you're seeing it cycle down upon seeing the pressure spike. Yeah, it's gonna be a carrier. Where did I put that schematic? It's an older carrier. Oh well. Can't seem to find where I put it. I'm just thinking. What else could we do? Like, what else could we check? Really love to get that schematic up so I could just kind of stare at it for a second, see if anything pops out to me as, oh, let's do this. That's not right. Okay. So I can clearly see in the trend that the condensing pressure actually reaches 23 bar and the mechanical high pressure switch is genuinely tripping. It's not a false pressure reading. Okay. Yeah. Now you're seeing the transducer correspond to the mechanical switch. Yep. If it was so being the fact that it's sporadic, I think Jason mentioned like non-condensables. Non-condensables would be consistent. It's not going to be just a sudden. Yeah. Even if it was oil logged, hang on, I can clearly see that the trend actually reaches sudden high pressure spike. Because even if we were having some kind of weird oil log condition, that would happen gradually. That's not going to happen quickly. Fans are maintaining. I mean, that's a good point. Yeah. What is our low side doing at the same time that the high side is spiking? That's a really good point. Now, are we gaining? Because again, we got to think about things that could happen in a fairly short order, right? So things that are going to be fairly consistent. So non-condensables we can fairly well rule out. Um, Filter dryers we can rule out. Now you said you can see it in the trend. You said the fans are all running 100% when the issue occurs. So, which I'm assuming you've physically witnessed this happen, but you said even when you shut the fans off, it still takes time. So, that's not, yeah, that's not happening sudden enough, which is true. Like it takes time. Like I've had to do that test before myself. Like that was my same experience. It's not just an instant within a few seconds. It takes. There's a kind of a window where the heat has to build up enough in the coils, and there is this kind of gradual rise in head pressure until it eventually trips. It's not just a sudden there. Um, Yes, Miss Lisa has entered the chat. Goober, making a mistake? Where did I make a mistake? Can clearly see the trend. So in the unloading process, so I mean something is causing a spike in the first place to because even so that's the thing, even if the EXV save failed and was closing suddenly, um, yeah, even if the EXV failed, it's the same. It's a similar condition as to like shutting the fans off. It's not going to be an immediate trip like that. It's going to take a second to build enough head pressure to actually trip out. Unless it's a freaky physical thing like chiller is located down, delivery truck parks a. It sounds like some experience there, Sterling. Yeah, no, I really want to figure this out. Let's stick with it. I wanna see if we can come up with some good. Yeah, is there an economizer? I mean, it's a fair point. Like, do we have some kind of economizer package on this machine? I think Sterling has kind of asked that a couple of times. And keep in mind, Marco, like we're not trying to like pressure or anything. Our goal here is just collectively as a community. We're just trying to think through and talk through. Um, and there is everybody keep in mind like um, there is a pretty significant delay in terms of like what I say to y'all commenting to like everything being on the same page. So we do need just a little bit of patience in uh, keeping that in mind. It almost feels as if the compressor is pumping against a closed valve. Well, so that's the thing. If the check valve was checking, which is internal to the compressor, we would we would end up having a we'd end up having the compressor, like that does happen very quickly. Like within just a matter of seconds, we have that pressure spike and the compressor begins to kind of just, we call it surge, even though I don't know that's truly the most accurate term. But it begins to surge the way it does, the way a screw can if it has restricted discharge flow. And uh, but we wouldn't see it on the pressure. Sorry, I've got too many lines of thought going in my head. We wouldn't see it on the pressure. So, like being the fact that our discharge pressure is spiking via the transducer, which is after our check valve, we wouldn't see that pressure report there. Basically, that pressure would just kind of stay stagnant is usually what I've seen. It won't really move all that much, but all of a sudden we'll start hammering and surging at the compressor and then trip out, which most of the time, again, I don't remember where the high pressure switch is on this machine. But I know typically they'll put it down at the actual compressor housing. So I'm assuming the pressure switch itself is on the discharge side of the housing, with the transducer being downstream on the line just a little bit. Yeah, Grady's point on checking both coils. The switch is on the discharge line after the check valve. Okay. Yeah, I mean, verifying the wiring is a smart step. Part of our issue that part of issue we have is that we have multiple things kind of trending in the same way. We're seeing he can see via the log trend that there was a sudden spike in head pressure. At the same time of that spike, there was the high pressure switch. Yeah, the unit was in heat recovery. RTF 245, one compressor circuit. Yeah, both compressors are VFD driven. Right, which eliminates the question of, because I've had that before where the slide valve, the load and unload valves were having an issue, and it would randomly, the load valve would randomly stick and slam the slide to max, and it would trip like that. Which again, being your VFD driven, that's not the case here. That those don't have a slide, which those also don't have variable indexing either. Ooh. Do they? No. No. Maybe y'all can confirm this, but yeah, those RTAFs, they don't use a volume indexing control. So they don't have they don't have an additional set of solenoids on the compressor. Yeah, Grady's saying he's had several high pressure faults on the 454B due to bad switches. Yeah, part of what I know we're struggling, because again the controls obviously sees it because it ramps down, but that's the thing I'd really like to confirm, Marco. And again, none of this is to challenge you; it's just help us understand the situation. Have you seen it trip in front of you? Like, have you been standing at the machine, or are we strictly relying on fault logs? Like, is it strictly in the fault logs that we're seeing this data? And the reason I bring this up is because I've had way too many scenarios where the fault logs aren't quite perfect, and they can be imperfect just enough to be very misleading. Yeah. So I just, again, I'm not challenging your work. I'm trying to have you physically seen this trip happen in front of you. Uh, hmm. Think. Because it's not gonna. It's trying to slow the compressors down, so it sees that we have high pressure. It's going into some kind of like high pressure limiting. It's trying to back off due to the high pressure condition. Well, in terms of the A2Ls, like having common switch failures, that to me that gets back to just a materials issue. Like the materials we're using is the materials we're using just don't react as well to the current refrigerants. But we've seen this before, right? We had similar issues when we switched from R11 um, to 123. We had similar issues going from R22 to 410A beyond just pressure issues. There was oil changes. Like it's just part of those curves we got to get over. Wasn't on site when it happened. I'm only looking at the trend logs, but they clearly show the condenser pressure reaching 23 bar, and the mechanical high pressure switch actually trips. And to your point, um, and so the only other thing I would want to know from the log is how often it's taking a trend. So is it every 5 seconds, every second? Yeah, because I don't know. I don't actually know from memory like how often that trend is captured, unless it was strictly the log itself at the point of trip. But so that gets back into, so if we haven't watched it happen, that's going to be a part of our issue. So we have to take this in context of we haven't physically seen the trip. You have shut the fans down. So I wouldn't rule out we having fans failing, because even though we've got the trend log, it could be that we could have fans intermittently shutting off, or a fan with a load on the circuit, and that causing a spike in head pressure and eventually tripping out. Like, in the log just not actually like tracking that correctly. See, could it be the compressor randomly going full bore for no reason and the fan's not keeping up? But that would be really weird. Symmetry. I mean, well, the compressor is going to be based on leaving water temperature, right? So our ability to load, unload, all that's based on leaving water temperature. So unless we just had a sudden spike in load and the circuit's trying to load up to capture that spike. Which, I mean, it's a fair point actually. Like, is this a site where that's possible? Could you or would you have sudden spikes? Even if we had sudden spikes, um, the system should not push itself like that. Like, so I guess even if there was a spike, that technically still shouldn't happen. Maybe check the VSD parameter settings on the fans. Yeah, make sure your differential isn't too wide. That's a fair point. Yeah, compressor out here. Yeah, it's full on going ADHD Holden style, just randomly wigging the fuck out. I had the same thing happen to me on a Daikin AGZ, but those Daikins have a solenoid to block off one of the coils in low ambient. I don't remember seeing one on the train though. Yeah, that's a good point. I'm not aware of train using that. That's a really good point. Thought about something blocking off the receiver that's in the middle, that's inside one of the coils, but then again, the low pressure doesn't seem to go down. There is a solution here, guys. So like we're coming up to it, and something he can try to verify in the field. All right, so he's standing there. He's got the machine in front of him. We're basing this off of what the trend logs we have at the time. It sounds like everything is fairly stable now, and it is just happening. It's happening randomly. So something is. The discharge ISO valve is confirmed it's not causing an issue. That's part of the issue with trend logs is what I find is a lot of the trend is recorded every second. So it's to a 1 second resolution. And you're seeing that within 7 to 15 seconds. So what the best solution here might be, if you could share with me that trend data, that might be our best path forward. Is actually getting that trend data and giving me a chance to visually see it and kind of go from there, because I'm curious to see like how is the machine, what's happening leading up to the point of the spike. You're saying, so I'm assuming what's happened is as the pressure, so you're seeing within that 7 to 15 second window, you're seeing the pressure increase suddenly and is rising up via the transducer. And in that process, you're seeing the compressor begin to back off simultaneously, and you're seeing the EXV adjust simultaneously. So these two things are being trended down to try to unload or pull load off of the circuit because the pressure is suddenly increasing. Which, for the pressure to suddenly increase, that means that we're able to see it at the transducer increasing. So whatever is happening post transducer in the circuit. The train commercial sneaking out in the middle of the night. Yeah, it sounds like it's probably stable operation, but it's a fair point. Is this right at the time of startup, or is this happening mid operation? That's a fair question. You've already tried shutting the fans down. That takes longer than the trend showed the pressure rise. I don't think it'd be an oil issue. The Which, I mean, if it was at startup, the trend would show that the circuit just started. So that we should be able to see that via the trend. Was this within the first 30 seconds of operation, or was it after that? Oh. Yeah, even if the EXV was to close, that would still take, I would expect that to take more than 15 seconds. I would expect it to. That's assuming the valve actually closed. I mean, I don't know. I mean, if the valve opened at all, something would have had, like the control module would have had to tell it to close. So it's not just going to randomly close on its own. Something had to tell it to. Sudden spike in pressure causing high pressure switch trip. While it could be a condenser fan, it's not a fast enough response. While it could be an EXV, again, not a fast enough. We have a troll in the chat, everybody. I'm not aware of anything else in the circuit that would cause this a problem. And again, we've got pressure transducer and mechanical switch corresponding with each other. So, like, in terms of, are we confident this event is happening? Yes. If it was just one or the other, that would lead to questions. But we're seeing both happen together. A piece of copper debris plugs up the receiver from time to time. Would it trip on high pressure or low pressure first? I would assume that would cause low pressure issues before it caused high pressure issues, personally. See this issue in Munters when high pressure trips happen in 15 seconds when Y1 not energized, the reacting fan. Oh, he pulled it. Chris had a thought. Transducer might be reading lower than it's supposed to. Well, the point is, like, we are seeing the transducers take a spike, so we feel confident that the actual, like, these are great questions. We feel confident that the actual pressure is increasing, and it doesn't appear via the trend that it was a false mechanical trip. So then it becomes, if it's not a false trip, what caused the spike in the first place? Yeah. I think, let's see. I think what the best thing we can do here, I need to get into the trend logs, and I'd say, Marco, let's have a deeper conversation, and kind of talk through this. I would like to see this through as to, um, like what could be leading to this and what your overall conditions are on the machine. I know it's very difficult to. Could you're I would assume you're probably on site right now trying to deal with this, or you're on a site somewhere trying to deal with this while at the same time talk to us. Let's get into a spot where we can just more fluidly kind of communicate through this, and then we can do a follow up on stream. Um, yeah, we can do a follow up and see, like, talk through, even if we don't come to a resolution yet, at least maybe talk through and reapproach the conversation and go from there. Yeah, we're all invested now. Yeah, I know. Well, that's the thing. Like, guys, we're technicians. Like, this is what we do, and we do this because we enjoy it. At least most of us. If you don't, I'm sorry. I can't help you. But like, we're here because we have fun. You're not on this stream for the sake of being bored. So, like, I know we're bodying now. We got to know. We got to know. Yeah, not being there when it happens makes this really hard. And I've had such bad experiences with strictly relying on trending and not being able to replicate the condition at the time. So I just, like, it's not that trends are useless. I'm not saying that, but going strictly off of a trend is really hard. Marco, it doesn't sound like that's what you're doing. Like, you're trying to replicate this as best you can. Okay, so don't get me wrong. You're actively trying to replicate it. You're doing what I think the rest of us would be doing right now. It's just, it just sucks that the best information we have so far is strictly just what is in the trend, and that's a tough spot to be. Yeah, so Chris came back when a high pressure trip occurs, 15 seconds, calls not VFD energized, so it does not activate the reacting fan, or it applies to A1 compressor. Yeah, which causes a sudden spike. I'll be back on site tomorrow. So this is from Marco. I'll be back on site tomorrow to check a few things. I'll let you know what I find. Yeah, no, really enjoyed it, bud. Yeah, from absolutely, like, keep in mind. Well, this okay. This was fan running in reverse intermittently. Um, I've not seen that happen on an ECM like that. Uh, so I guess I never would have considered that. I would lean towards less likely. I'm not going to say not possible. I would say less likely. It's the right question though. Like, these are the questions we should be asking, especially now that we're getting off into just the unknown abyss of troubleshooting that we find ourselves in. These are the kind of questions we have to start asking. Like, I just had this conversation with a engineer, because I've been so what we can I've been trying to work on how to better explain choke from a centrifugal standpoint, and so I've got kind of this more technical explanation as to what's happening and the sound barrier and all the stuff that happens when choke occurs and how we're creating shock waves and yada yada yada. So, I send this to one of my engineer friends and be like, "Hey, how does this explanation sound from a choke perspective?" And he basically is just like, it's fine. I don't know why it matters. It rarely ever happens in the field," which is true. It's absolutely true. We rarely run in a choke condition. So he just had this very and I'm not calling him out. I'm just kind of, it just makes me chuckle because these are you just we get into these things, and so we're trying our best to troubleshoot this thing like a madman, and uh, banging our head into the side pillar of the system, and just we have to start getting these really weird questions of could this be, and so like it makes me think of like, he's not done the now he is a technical engineer. He has been involved in live machine process troubleshooting, like and not to minimize his what he has done. At the same time, his he comes at it from an engineering perspective, and from an engineering perspective, choke is a very non-consequential issue for the most part because we don't really operate there. But my point to him was from a technician's perspective, we know it exists. We know that it can be an issue. And when we run into stuff like this is a prime example. We hit these points of just WTF. We have to ask every question in the book at this point just to try to get somewhere. And so it's like, okay, well, at least if we understand how to properly interpret what this thing means, we can better rule out the possibility of could it be this thing. And so in spite of how unlikely it is, we find ourselves routinely in a position to where we just have to ask every possible question. So, yeah, it makes me chuckle inside. Appreciate you being the guinea pig for today, Marco. And hopefully we're saying your name correctly. If we're not, feel free to correct us, because I'm not very good at that kind of thing. Yeah, and I will say, yeah, Train R series, right? So the Train air cooled line. Now I will say, RTAFs and the ACR series, all of the newer Train air cooleds, to be frank, I've been less impressed with. Like the RTAE was not so good for Train, but overall, the Train screw lines have been historically really, really, really good machines. And Train, to their credit, even on their newer machines, has done a lot of work to improve many of the issues that they've had over time. So I am a fan of Train screw machines in general. Train does a good job. They're not perfect, but they do a good job. And I would say that they run into the same stuff that everybody's running into, where we have these efficiency requirements we have to hit, and that means we have to push the boundaries of what's possible to such extremes that it's just inevitable that we're going to start running into some of these wild, crazy issues, which is what we see. So that's just the forcing function of having to hit certain metrics deemed by other people, like the regulatory bodies, the EPA, here in the States at least, like as a whole, they're forcing that these things happen and you have to hit these numbers and da 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 da. Yeah. Yeah, they built their reputation on the RTAA, AC, and RTA variants, but now having to change because they're exactly right. And that's the thing. Like they took like the RTAA and AC, the RTHD. Like the RTHD has its problems, but overall was still a phenomenal machine. Those three were like they were incredible to this day. Absolutely incredible machines. Could not love them more. And I think Train is going to get to the other side of this, because it's not just them. Like everybody's had issues with this. York's had their issues. Carriers had theirs. Daikin's had theirs. Like everybody's had their own issues in trying to figure out how to hit these current metrics. It's because they're having these efficiency numbers pressed on them in addition to all these refrigerant changes. Like it's just, I'm making excuses for them at this point. It's a lot. So I can give some grace as to why things have gone the way they have. Do we have hot gas bypass stuck open during the refrigerant into the suction line? Hot pressure. Good question. RTAD. Yeah. Okay. Let's see. Do we have time for another question? I think we may try to squeeze one more in. Let's see. Yeah, let's do that. Let's do a YKEP. Let's change this up here. We'll hit this one today. All right. Are the condenser and economizer liquid valves both variable orifice on a YKEP? Yes, they are. So if we come down here to our schematic, this is a YKEP, so it's a York centrifugal with an economizer circuit. Now this is not some other, like we've got the YKCP that just hit the market, which was their two-stage machine, which means we have a two-stage compressor, and its economizer is doing the same thing basically everybody else is doing. What they did with the YKEP was they kept the single-stage compressor and they installed a economizer compressor just to manage the flash gas. So we're using a flash tank economizer with this style. Uses all the same fundamental principles that a flash tank does. So I've done several trainings on this in my online certification course at Chiller Academy. Like I have an entire lesson dedicated, or entire module, much less lesson dedicated to explaining how these work on an in-depth scale. Ultimately, the control valve for the variable orifice on the economizer is right here leaving the condenser. So then we have the condenser economizer control valve, and then we have the or I'm sorry, I said this backwards. We have the condenser control valve, then we have the economizer control valve. And keep in mind, the way York is controlling this is we're monitoring liquid level on the condenser, which is the same thing we do with a YK, but then they're also monitoring liquid level in the economizer. And so that is what these two valves are balancing for. First, the condenser is going to maintain a certain level because we have to be above this subcooler rack. So we come in, superheated discharge gas, we have to desuperheat, we have to saturate down on these middle tubes, and then we subcool with these lower tubes down here. So our liquid level should float right above this subcooler rack assembly in the bottom of the condenser, and that's where your sight glass is going to be, is right about here. So you're going to see the top of that rack. We have to maintain just above that in order to prevent too much turbulence, yada, yada, yada. Okay. So while this is maintaining, we have a variable orifice valve that is controlling the flow going into our flash tank. Now keep in mind, this is a medium pressure. So we have high pressure liquid leaving the condenser, medium pressure saturated vapor liquid mixture in the economizer. Liquid falls to the bottom as a medium pressure, fully saturated liquid. Vapor leaves out the top, coming into the economizer compressor, which is another little small centrifugal, right? So they're using just a little mini centrifugal and a big centrifugal. And so that is cycling the medium pressure back up to high pressure vapor. And then we take that medium pressure saturated liquid and we process it through another variable orifice valve. So both of these are variable orifice, both of these are controlling to liquid level. So we have another liquid level control sensor in the economizer chamber, which then tells this valve open, close based on that level set point. Just like what Train has done with an RTHD as an example, right? That's all these are really doing. Just we're doing it on this side of the circuit instead of the evaporator. Okay. Or an RTAC, they're doing the same thing with an RTAC. Anyway, so then based on the level in here, we then feed into our evaporator. So the If everything's charged and balanced correctly, then our evaporator liquid level is just a byproduct of maintaining proper condenser and economizer level, which the benefit to that is by maintaining level over here, we ensure maximum efficiency, or effectiveness would be the more appropriate term, of the refrigerant in the evaporator. Whereas if we prioritize evaporator level, yes, we may maintain coverage on the tubes, but we risk losing the maximum efficiency of properly processing that refrigerant. So York makes the trade-off that they want to maximize the effectiveness of the refrigerant by controlling the condenser and economizer side of flow, and then the evaporator should be the byproduct of that happening correctly. Whereas others, not just Train, but as others, by monitoring the evaporator level and controlling for that instead, we are ensuring that we are fully covered in the evaporator, but there is a risk of if the system's not balanced correctly, there's far greater risk of not having as efficient of refrigerant in the evaporator, even though everything may be fully covered. And that's a big part of the logic reasoning behind York doing one over the other, as an example. So let's see, just kind of catching up on the chat here. McQuay, screw, yes. All right, we'll circle back to that in just a second. So anyway, that is your variable orifice valve on both the condenser liquid line and then the economizer liquid line. Both of those are variable orifice, same type of valve assembly. And the main difference, this is a larger machine. They're just using a larger valve. So keep in mind that York, when we say a variable orifice, the York is using it looks like a butterfly valve, but it is modified. It's not just a normal butterfly. And that's what they're using to open and control the flow based on these levels, right? And it's still doing the same functions for pressure drop and flow control, right? So we're still controlling flow. We're still creating a pressure drop across the valve in the process. We're just doing it with a different valve design. So instead of trying to make a huge EXV to operate at this level, which are more prone to failures, where these variable orifice have proven to hold up really well, or having going to the Train route with having just fixed orifices, there's trade-offs that with fixed orifice. While a fixed orifice is less likely to fail and it's more reliable from that standpoint, it doesn't have the precision of control that a variable orifice would, so that when we do need that, when we would benefit from those valves closing down and restricting more for the part load conditions, like we're not going to get those efficiency gains with fixed orifices that we do get with a variable orifice. And so there's just all these trade-offs that we're going for. That's where Train really makes their standpoint on, we are the reliability king. Our focus is everything is built for simplicity and reliability, and Train puts a lot of engineering behind that, despite how it feels sometimes. Whereas York, they make their standpoint on, we are the efficiency king, and everything we built is to maximum efficiency, but that comes at the cost of some reliability. So that's just my perspective, at least, having worked with both brands for quite some time. So, okay. We're going to wrap that up there, guys. I will grab this other question here. I will get it added to our list. If there are any other questions, feel free to go ahead and get them added now. I will save them. With that, y'all have a great week. Take care of yourselves. Be safe. Make sure you're drinking plenty of water. And MTT, make the time for your family, for your spouse, for your kids. They really, really need you.